So today we're going to begin this first lesson on waves and vibration, a new unit here. Let's see what our objectives are. So we're going to describe and give examples of something called periodic motion. And then take that a step further, a little more specific, of simple harmonic motion. And what are the two properties or requirements for us to have simple harmonic motion? And then the third step is to understand how a pendulum and a mass on a spring are examples of simple harmonic motion. And then last, we're going to look at some basic math that we use to describe simple harmonic motion, which can be modeled as a wave. So parameters like wave speed, wavelength, and frequency and period. All right, so first let's define periodic motion. So periodic motion is any motion that repeats in a regular cycle. So here's some examples, right? A ball bouncing up and down, or grandpa going back and forth in the rocking chair, right? Or the pendulum of a clock swinging back and forth, right? These are all examples of periodic motion. It's a motion that repeats in any regular cycle. Now, simple harmonic motion also has periodic motion, but there's two other specific requirements. It occurs when a restoring force on an object is directly proportional to the object's displacement from equilibrium. So here's some examples. We have a mass on a spring, right? It has periodic motion. That's the first requirement. But the second is that it has a restoring force directly proportional to the object's displacement from equilibrium. So at some point, right, that weight on the spring is going to settle down and reach an equilibrium point. Now, if we pull that spring below that and let it go, it's going to move upwards, right? The spring is going to get stretched out and want to pull the mass back. So there's a restoring force back towards the equilibrium. Or if we lift the spring above its equilibrium point and compress the coils of the spring, when we let go, those coils are going to want to expand and push it back to its equilibrium. So that's the restoring force that we're talking about. So in this case, the equilibrium would occur, right, where the force of the spring pulling up is equal to the gravitational force on the mass pulling down. Well, let's look at another classic example of simple harmonic motion, the pendulum. Okay, so where is its equilibrium position? Well, it's going to be right in the center, right? If you eventually let that pendulum swing and die down over time, it's going to come rest hanging vertically, right, straight down. So what provides the restoring force? Well, as we lift the pendulum up, either to the left or to the right, we can draw in some forces that are acting on that pendulum. So a pendulum hanging by the string is always going to have a tension force pulling upwards, and gravitational force will pull straight down. Now, in the center, right, gravity and tension force are equal to each other. So it's going to be in equilibrium. But when we're to the left or to the right, we can take these two vectors and add them together and find the net force. And notice that that net force is directed back towards the equilibrium position. So that's the restoring force. The gravitational force combined with the tension on the string produces the net force that pulls the pendulum back to the center. That's what provides the restoring force. So the two attributes for simple harmonic motion are its period, and this is the time required for one cycle of an object that's moving in simple harmonic motion. So for a pendulum, that would be the time it takes to swing from the center to the far right, to the left, and then back to the center again. That would be one complete cycle. The other key attribute is the amplitude. So the amplitude tells us the maximum distance an object moves from equilibrium. Okay, so how far does it move to the left of center or to the right of center? That would be the amplitude. So let's go back and look at these three examples and see, are any of them examples of simple harmonic motion, right? They're advantages of periodic motion, but do they have a restoring force that causes the moving object to move back to its equilibrium position? So the first one, the bouncing ball, the answer would be no, right? Because its equilibrium position will eventually be sitting on the ground or the floor, and it's bouncing above that, but not below that. So we would say no. How about a rocking chair? Well, yes, right? We can rock back, and then if we release, we're going to rock back to an equilibrium position. If we rock forward, we're going to rock back to the equilibrium position. So that would be yes. And a pendulum, right, is what we just talked about. Of course, that would be simple harmonic motion. All right, so how can we model this simple harmonic motion? Well, look at this object that's moving up and down. That would be like the mass on a spring, okay? And if we plot its motion vertically up and down, so its amplitude, how far above and below the equilibrium position, the dashed red line here, is moving versus time, we generate what we call a sinusoidal wave. Okay, so those of you that are in trig or calculus, you've done a lot of work, right, with our trig functions, sine and cosine. When we graph them, produce a nice smooth wave. And that's exactly the same type of wave we get when we plot amplitude versus time of an object that's moving in simple harmonic motion. So going forward at this point, we're going to use a sinusoidal wave as a way to mathematically model simple harmonic motion. So the amplitude again would be from the equilibrium position to the maximum above or the maximum below. And then time, right, is what we're plotting on the x-axis. So let's draw a wave that's not moving on us. And we're going to label some key attributes here. So we've already talked about amplitude, right? The distance from the equilibrium point of the wave. So how far above or how far below that is. The other key attribute is going to be the wavelength. Okay, so the wavelength is the distance that the wave disturbance travels in one period or cycle. Okay, so notice we have a new symbol for wavelength. It's the Greek letter lambda. It maybe looks like a Y upside down. And this is the symbol we will use for wavelength. And wavelength would normally be measured in meters or centimeters. It's basically a measure of length or distance. Another important attribute is the crest of the wave. This is the point where we reach the maximum positive amplitude. Okay, so we have in this example 2 crests, and then the trough. The trough is where the wave reaches its maximum negative amplitude below the equilibrium point. So those are the key parameters, right? Amplitude, crest, trough, and wavelength, all things we can label on a sinusoidal wave that we're using to model simple harmonic motion. So a little more formal definition now. The period is the time required for the wave to travel through one complete cycle. Right? We just talked about that a minute ago when we were discussing the pendulum. The symbol we're going to use for that is a capital T, and the units will be in seconds. The frequency is the inverse of the period. And so, whereas period is the time required for one wave cycle, frequency is the number of cycles that can fit into 1 second, okay? So they're inverses of each other. If we can find one, the period, then we can easily find the other, the frequency. The symbol for frequency is a small f. Remember, capital F is for force, so we're going to use small f. And then the units for frequency is called a hertz, H-E-R-T-Z. And you'll see that abbreviated as a capital H and a small z. And that is just the name for the units that is really cycles per second. Because remember, frequency is the number of cycles that occurs in a 1 second time period. All right, let's apply this to an example. So a metronome, if you play a musical instrument, these are little devices that basically are based on a pendulum, kind of an upside down pendulum, and they swing back and forth. And as we change the length of the arm, moving that weight up and down, we can change the speed that it does. So musicians use these, or used to, we probably have electric versions of them now, to set a certain tempo or pace that you're playing the piece of music at. So what does it tell us? It says it makes 10 complete vibrations in 12 seconds. So I'm asking you to find the period and the frequency. So remember, the period is the time for one cycle. So time over number of cycles. So we're going to take the time of 12 seconds divided by 10 cycles, and it works out to about 1.2 seconds to make a complete cycle. For frequency, remember, it's the number of cycles per second. So we're just going to take the inverse of that ratio. It's going to be 10 cycles divided by 12 seconds, and we get 0.83 hertz. Okay, so these values should be inverses of each other, right? 1.2 seconds, if we find the corresponding frequency, would be 1 over that. And so we would get 0.83. So if we find one, we can easily find the other by simply taking the inverse, taking 1 and dividing it by that value. All right. Let's talk about the speed of the wave and the difference between wave speed and wavelength. So wave speed is related to the wavelength and the frequency. And we use an equation we call the wave equation. Okay, so wave speed is equal to the wavelength times the frequency. So lambda times f. Remember, lambda stands for wavelength, small f for frequency. So we're going to use this equation a lot. Okay, it's one you're going to have to get comfortable with. But it tells us the speed at which the wave moves based on its frequency and its wavelength. So let's look at an example. Say we have a wavelength of 3 meters and a frequency of 1 cycle per second. So that means every second, right, a wavelength is going to pass by. So how long is the wavelength? Every second it's going to move 3 meters. So if we multiply those together, we're going to get a wavelength of, or I'm sorry, a wave speed of 3 meters per second. Okay, so wavelength times frequency equals wave speed. Now, in this simple example, right, we were solving for the wave speed, v, but we could solve for any one of the 3 if we have the other 2 parameters. So we could use this to solve for wavelength. We could use it to solve for frequency. All right, now, what is it that determines the wave speed of an object? So a wave is moving through an object, say like a rope that you're flipping, or a slinky, right? Big spring that we're putting into simple harmonic motion. The speed of the wave is not dependent on the properties of the wave itself. So in other words, frequency, amplitude, and wavelength. While we can use those to calculate the wave speed, that's not what actually determines the wave speed. The speed of the wave depends on the properties of the medium. So what is it traveling through? So things like its density or the tension on a string or a spring, right? If the tighter we stretch the spring, the faster the wave is going to move through that spring. Or the temperature, and then something else called elasticity, right? How easily does it return to its shape after we stretch it or pull it out? So the key here is that wave speed is determined by the properties of the material that it's moving through, not frequency, amplitude, and wavelength by themselves. So let's look at an example here. We have a slinky that we're going to provide a disturbance on, and we want to say which wave will reach the wall first. Well, doesn't look like there's any difference in the properties between these 2 slinkies. They look like they're both stretched out about the same amount, about the same size in terms of thickness. So we could assume that their properties are the same. So what is different is wave A has a greater amplitude than wave B, but does amplitude affect the wave speed? Right? because whichever one moves faster is going to reach the wall first. Well, since amplitude does not affect the wave speed, and everything else appears to be the same in terms of the properties of the slinky, then they're going to reach the wall at the same time, right? The wave speed will be the same in both slinky on the top and the slinky on the bottom. The amplitude does not affect the speed at which the wave travels. Let's look at another example. So wave C and D, what is different about these two? Well, C has a longer wavelength than D, right? You can see it's about twice as long, the disturbance there. But otherwise, if these slinkies are identical, we're going to have the same answer. The wave speed does not depend on the wavelength that is traveling through the slinky on. All right, let's look at a couple more examples and wrap this up here. It says, find the time required for the sound wave to travel from the tuning fork to point A. Okay, now I'm actually giving you the speed of sound, 340 meters per second. This is the kind of pretty close to typical speed of sound through our normal atmosphere at normal temperatures. And then we also are given the frequency. Now, a tuning fork, right, is a little metal device that will vibrate and produce a frequency. If you hold it up to your ear, you can hear it. And this particular one has a frequency of 512 hertz. And we want to know how long will it take it to travel the 20 meters. So in some ways, we can solve this problem very easily, right? Just going back to our motion equations, distance equals velocity times time, because we know how fast the sound wave is traveling. We know the distance that it needs to travel, and we're simply solving for the time. So we can plug those in, 20 meters divided by 340 meters per second, and we'll see that it doesn't take long at all for that sound to travel 0.059 seconds. Speed of sound through air is fairly fast. It's between 600 and 700 miles per hour. Now, two ways to find the wave speed, right? The first is the wave equation that we just talked about in the earlier slide, wavelength times frequency. But the other is if we're given the distance and the time. Well, the previous example we just did, right, really is using velocity, distance, and time. So it depends what information we're given as to which way we can calculate the wave speed. All right, let's look at a couple more examples here. If a water wave vibrates up and down 2 times each second, and the distance between wave crests is 1.5 meters, then I want you to find a variety of parameters here. So the first is the period, then the frequency, then the wavelength, and the wave speed. All right, now a good practice is to draw a picture. If you're not given a picture in a problem, sketch a waveform, your sine wave here, and start to label the information that we know. So what does it tell us? It says it goes up and down 2 times each second. Okay, so what is that information that they're giving us? So we have 2 complete cycles in 1 second. That sounds like frequency. Remember, frequency is cycles per second. The other information we're given is the distance between crest, 1.5 meters, right? So that's the distance to go through 1 complete cycle of our wave. So we're actually given 2 of these parameters directly in the problem. So, but let's go ahead and step through the other attributes in order. So the first is the period, right? What is the time for 1 cycle? It's going to be 0.5 seconds, because if it has 2 cycles, right, in 1 second, it's going to go through 1 cycle in ½ a second. The frequency is going to be 2 hertz, right? We can take the inverse of the time, or the way it was given to us, right? It goes up and down 2 times each second. So 2 cycles per second, 2 hertz. The wavelength we're given directly, right? 1.5 meters. And now we want to calculate the wave speed. So the wave speed Since we know the frequency and the wavelength, we can simply multiply those two together. We'll use that method to find wave speed, and we get 3 meters per second. All right, one more example here. Two boats are anchored 4 meters apart. They bob up and down, returning to the same position every 3 seconds. When one is up, the other is down. There are never any wave crests between the boats. Find the period, frequency, wavelength, and wave speed. Okay, so same things that we found in the previous example. So definitely, let's draw a picture here. Here's our boat on the waves, 2 boats. It says that they are 4 meters apart, so we can label that. They bob up and down, returning to the same position every 3 seconds. So that is our period, right? If it goes through one complete cycle in 3 seconds, they're telling us the period. So it's 3. The frequency, therefore, would be 1 over that. So 1 divided by 3 is going to be 0.3 hertz. So 1/3 of a cycle every second. Now, it tells us that the boats are 4 meters apart, but when one is up, the other is down, and there are never any crest between them. So the distance between the boats actually represents a half of a wavelength. So if a half a wavelength is 4 meters, the full wavelength is going to be 8 meters. Now, that's a typo on my slide. That should be 8 over there, but I show it 8 on the left. And then the last part, again, we'll use our wave equation since we know the frequency and the wavelength, and we multiply those together and we get about 2.6 meters per second. All right, so that's it. That's our first kind of introduction lesson to waves and vibration. We're able to describe and give examples of periodic motion. We can define simple harmonic motion and the 2 properties that describe them, right? Their amplitude and their period. And then we understand that a pendulum and mass are examples of simple harmonic motion. And we know how to mathematically relate things like wave speed, wavelength, and frequency.